Okay, hey, we're going to take a look at a very important. It's all important. What can I say? But these are a couple of fascinating topics, a couple theorems. One is really a special case of the other, but it helps us later with integration and building our knowledge in that subject area. So this section is pretty quick. The homework's kind of quick. It deals with Rolle's theorem and it deals with what we call the mean value theorem. I write in here that Rolle's theorem is actually a special case of the MVT. And then there's an important corollary to go with that. So let's look at Rolle's theorem first. Rolle's theorem says, and look at the hypotheses right here, the function f is continuous on, the hypothesis is if the function is continuous on a closed interval a, b. Notice that this is closed. And it's differentiable on an open interval a to b. Okay, doesn't have to be differentiable at the endpoints, but it does have to be continuous and differentiable. And then the third one is f of a is equal to f of b. What's the conclusion? Well, there's a number c. Well, let's not even read the conclusion. I tell you what, let's look at a picture. So you got a coordinate system, right? And you got some sort of function moving through space like that. And it turns out that at some value a, and then if we read way over here like this, there's also some value b such that their function values are equal to each other. So f of a is equal to f of b. Not only that, try to get the green this time, the curve is nice and continuous, okay? And it's differentiable. If all three things hold, then there's a number c such that its derivative is 0. Can you imagine that number? I can. The derivative being 0 means m tan is 0, so right about this guy, right about here maybe, it's got a 0 tangent. It has no choice because the curve goes up. In our case, it goes up and then down, and they match at the endpoints. It could have been the curve goes down and back up again if you wanted it to, but this is what Rolle's theorem is all about. All three of those conditions have to hold. So it makes sense. It also makes sense that it has to be continuous, because if I drew a picture here and the same story is happening, say I've got the curve doing this, it's got an asymptote, it drops down. You know where I'm going with this? Is it has maybe this is A, okay, good. And over here is B, okay. But do we have a C in between them where the derivative is 0? No, because it's right here discontinuous. So now you can see it has to be continuous, okay? It has to also be differentiable. You could have something like this, and the one thing to play around with is maybe a cusp, okay? And once again, say this is A, and this over here is B, and their function values match up. F of A equals F of B. But in between, what do you see? I see a point of non-differentiability. The derivative doesn't exist there. So that's where you have to have it be differentiable. So those two topics, those two hypotheses have to hold. And then, of course, have the endpoints equal to each other. So let's play around with this guy. Here's an example of how to do this. So verify that f of x is x cubed minus 2x squared minus 4x plus 2 satisfies the three hypotheses of Rolle's theorem on this interval. So they give you an interval, and they give you a function. So this is a and b, and this is f of x. Pretty simple. It says, once you do that, so we verify it, and then when we're done, we have to find the number c, there might be more than one, that satisfy the hypothesis. I think I stole this from the book maybe. Anyway, one, f of x is a polynomial. It is x cubed minus 2x squared minus 4x plus 2. Hence, it is continuous. In fact, it's continuous on R, so whenever you see a polynomial, it's super easy. 2, it's also differentiable on R. Not just A to B, not just minus 2 to 2, but everywhere. Here's the third one. Here's the thing. does f of a equal f of b? So in our case, that means does f of minus 2, see where I'm picking that up, equal f of 2? Okay, so f of minus 2, I haven't done this problem, so I got to do it. On this side, well, I'll write it. F of minus 2 looks like it's minus 8, and that's a 4, so it's minus 8, and that's going to be plus 8 and plus 2. What did I do wrong here with this one? Minus 2. Oh, okay. So what we're getting is, looking like a minus 6. Okay? So what's f of 2? F of 2 is 2 cubed is 8, and then minus 8, and then minus 8, and then plus 2. And guess what? It's also equal to minus 6. So it satisfies all three. Well, that's good. So the next part is find the c that takes care of that. So what we do, we have to find c in AB. Actually, it should be probably open interval. We don't want to include those guys, such that f prime of c is equal to 0. Okay, so we have to find the derivative. So the derivative of this guy, first of all, find the derivative. And the derivative is, looking up here now, 3x squared minus 4x minus 4. And we're looking for the c that has a 0 derivative. It's pretty straightforward. It's basically, I'm looking to see where you have a horizontal tangent. But one is guaranteed by Rolle's theorem to fall in the interval minus 2 to 2 because of the hypotheses. So we set this guy equal to 0. Looks like we're going to have to factor. So 3x, it could be 2 here and a 2 here. That would be minus and a plus maybe, right? Okay, so we're getting x is negative 2/3, and we're also getting x is equal to 2. Okay, well, that's interesting, right? Those guys worked, right? I got 3x squared, I got minus 6x plus 2x minus 4. Yeah, so if you look on the interval, here's the thing. The interval that we're looking at is minus 2 to 2. Now I got this weird thing about maybe it should be open interval, but maybe it should be closed. I wonder what the hypothesis says. Doesn't matter. We found two guys. We found one of them is here, minus 2/3, and one of them is actually the endpoint at 2. So we're going to state it, that's our C. Oftentimes they go, okay, so the C in the hypothesis is this. And that's a look at Rolle's theorem. Okay, one example of that. Polynomials, there you go. I think I'm kind of in a hurry, though, to look at the mean value theorem. The mean value theorem, and you can pause and rewind that. Let me go back to that. Let's respect that a little bit more. Because we have a picture like this, and it's actually minus 2, and over here is 2, and they matched it minus 6 down here somewhere. So what happened, I guess, apparently, is it could have gone, I don't know which way it goes, could have gone up and hit a 0 minus 2/3, and then at some point cruised along. Well, it could have gone, well, I think it, I don't know what it did. Let's pretend it did this is me not going above and beyond. It probably starts here and maybe cruises down and then swings, who knows. Oops, this guy would be down here too. So he probably swings, but he has a 0 tangent there. So maybe it does something like that. What do you think? 0 tangent, 0 tangent. Okay. All right, so go back to the mean value theorem, a little bit all over the map here. The mean value theorem is a little more robust. It just says that f is continuous on AB and differentiable on the open interval AB. Then it says, a little more loose, it says there's a number c in AB such that its derivative is equal to the slope of the secant. Yeah, that's the difference quotient. So a picture of that is really cool. We'll go, I've got a function that I don't know what it's doing. It's cruising along like this. You got an A here, maybe a B here, and here's what it says. It says it's continuous, right? I drew a continuous curve. It's differentiable, sure. It's going to be this guy from this point to this point We are calling that in the class m secant. You don't have to, but that is f of b minus f of a all over b minus a. Another thing I called it was like average velocity. But apparently, if you use your graphing skills imagination, there's a c in here whose derivative, that is its instantaneous velocity, or m tan, or f prime, evaluated at c, is equal to the same slope. See how I drew them as parallel as I could? That's possible because it's a continuous curve, and that's where you're getting this result. Okay, so I'm trying to cram this into one video, so I hope that you can see what happened there. You can rewind it and go, what did he just say? He said that the slope of the tangent somewhere between a and b, call it c, is equal to the slope of the secant connecting the two endpoints a and b. And that's how we can write it in calculus. Pretty cool. There's an all-important corollary that happens to be important to us towards the end of the semester when we're integrating, and I'll just state, it's stated here. It says, if you have two functions where f prime of x happens to equal g prime of x. Okay, that's interesting. That means for all x, let's say let's say for x on an interval a to b maybe. Usually it's just all real numbers. But what happens is that these guys, if they have the same slopes, like for instance, you can draw a picture of this. You got a G curve doing its thing, and maybe this is A, and way over here is B maybe. Well, the F curve has to have the same slopes at every point. So it would look, I don't know, mimic G, but they would differ by some sort of constant. Only a constant difference. So that seems trivial, but it's really important to us later. If you have two functions whose derivatives are equal to each other, then they differ by a constant. So you could say something like f of x, it implies f of x is equal to g of x. So if the derivatives are the same, the functions are the same, but they might differ by a constant. And we'll later call that the constant of integration. Okay, so let's look at this in action and we'll wrap up our video. I think that's all I have for us. Yep, two examples of the mean value theorem. Let's work on this one first. First of all, you can notice that it's a polynomial, in this case, is continuous and differentiable everywhere. In fact, is that the same problem we just did? I don't know. Okay, so the hypothesis, so it's definitely continuous and differentiable on our interval -2 to 2. Okay, so all you have to do then is, well, we're going to take we have x is equal to -2, f of -2 is equal to, you go up to the function, it's -8, and then +6, and then +2. Apparently it's equal to 0. And then if x is equal to 2, we're going to get f of 2 is equal to 8 minus 6 plus 2 is 4. Okay? So here's what I'm going to do. I'm going to write this out. I'm going to go f of b minus f of a all over b minus a. In our case is 4 minus 0 all over 2 minus, am I doing that right? Minus, yeah, I'm going 4 minus 0, that's the y value. In fact, you can, maybe helps you to see it this way. I've got x and I've got f of x. I've got a table, -2 gave us 0, 2 gave us 4. So I'm doing the slope. I'm just going 4 minus 0, -2, 2 minus a -2, and what we're getting in this case is 4 over 4 equals 1. Okay, that's important to us. Well, apparently, in the interval from -2 to 2, there's some sort of c value somewhere that has the same derivative, has a derivative that's the same as equal to 1. So we have to take his derivative. We take f prime of x, we derive it, 3x squared minus 3. And this time we don't set it equal to 0. We don't do that. That's Rolle's theorem. We set it instead equal to the slope we got between the connecting points, 1, and then we solve this. So we get 3x squared is equal to, say, 4. So x squared is equal to 4/3, and yeah, we got to do it. X is equal to plus or minus, say, 2 over radical 3, which is, you know, a little less than 1. Well, the interval we're seeking is between -2 and 2. And I think we'll find that they both fit. I mean, -2 over radical 3 could be here, and 2 over radical 3 is here. So they're both in the interval, so we're going to say we have, well, actually, let's use c. We have two c values, so to speak. We have c is equal to plus or minus 2 over radical 3. And in my class, don't bother rationalizing the denominator. Okay, that's that one. Okay, pause it and look at it. Again, though, the steps are, hey, I'm going to take the endpoints and plug them in and create a slope. Then I'm going to take the derivative and set it equal to that slope. And then I'm going to solve for x. And then I'm going to decide which ones are in the interval. Okay, let's do one more. This is getting kind of lengthy. This is interesting. All right. One more time with feeling. If we take f of x is equal to 1 over x, you know, it is actually discontinuous and also non-differentiable. Oh. At x equals 0. But notice that the interval is 1 to 3. So we're talking, here's 0. That's a problem. But we're going from 1 to 3. So we're okay. That means, all right, so do the table. Here's x, and here's f of x. And I'm going to plug in the endpoints 1 and 3. 1 gives us 1 over 1 is 1. 3 gives us 1 over 3 is 1/3. And then I'm going to find the slope. M is equal to 1/3 minus 1 maybe over 3 minus 1. So we're getting a negative 2/3 over 2, which is like 1/2 to, I think it's a negative 1/3. Okay? All right. So now we take the derivative of this function, which is, I'm actually taking 1 over x and deriving it, which is like deriving x to the negative 1. So what we're getting is negative 1x to the negative 2. Better way to write that might be minus 1 over x squared. You know what we're going to do? We're going to set it equal to that secant slope. Okay, I'm going kind of fast. You see what's happening? I'm going to lop off the negatives. Okay, so now I have 1 over x squared is 1 over 3. I'm going to flip them over. X squared is 3. I'm going to square root x is plus or minus radical 3. And now look at the interval again, 1 to 3. And we're not interested in the negative this time. What we really are interested in is the negative radical 3. So the answer, c is equal to positive radical 3. Positive radical 3. Oh my goodness. And very quickly a picture of that. This guy's easy to scrawl. He kind of cruises down like that. And we're going from 1 to 3. And what we've got is a secant and then a tangent. In between here, we found the radical 3 gives you that derivative. And that's all she wrote on that. You can go back and go over it. I know I'm talking quick. I'm just trying to make a short video. We did several examples, and you'll notice that Rolle's theorem is simply a special case. It says that f of A is equal to f of B. So if I played this game of, okay, so here's x, and here's f of x, and here's A, and here's B, and I'm going to plug them in, you know what? I get the same number, whatever it is, call it m. And he gets m. So what's the slope here? M secant is equal to m minus m all over B minus A, which of course is 0. So that's why you set it equal to 0 with Rolle's theorem, because that's the slope of the secant line. It connects two points that have the same f value. That means it's a horizontal secant. So therefore, we're looking for a horizontal tangent. So Rolle's theorem is just a special case of this guy. And I'm going to end the video now. Enjoy.